Okay, we're going to carry on with the BJT amplifier, specifically the common emitter amplifier. We did an introduction yesterday about this amplifier. Let's just have a look at it again. There it is, figure 6.8, the common emitter amplifier. As we've said earlier, we've established already what type of biasing is used in this circuit. Based on the knowledge that you've learned in Electronics 1, we've seen then that I'm using voltage divider biasing. Ne? Voltage divider biasing. There are many other types of biasing that you also discussed, but we will talk about them again later. Alright, so voltage divider biasing, common emitter amplifier. We've established why this is a common emitter amplifier. Did we discuss that already? Can you still distinguish between the different types of configurations? Have we discussed that? We haven't. Let's just make sure again. Remember, we've mentioned the different configurations in the previous section. How do I distinguish between the different configurations? Is I go and have a look at my amplifier, on which terminal of the transistor is the input applied, on which terminal is the output applied. The remaining terminal makes it the configuration. Alright? So if I go and look here, I can see my input signal is applied at the base. There you know. Output signal is taken at the collector. There's my load. And here I can see via this capacitor that the emitter is connected to ground for the AC signal. No. Alright. So we've got a common emitter amplifier here. Look, where's the input, where's the output. The remaining terminal makes it the configuration of amplifier. I will also show you later on when we get to the common base and the common collector amplifiers, just again, so to how we get there. Right, another thing that we also didn't look at yet is what is different from the circuits that you've discussed in Electronics 1 is the capacitors that we see here. Ne? So the capacitors, I can see there's a capacitor C1 and a capacitor C3 and a capacitor C2. I have to know, of course, how does a capacitor behave under DC or AC conditions. What does it do under DC? Axis is short, nah? So the current will flow through, but for AC, it will block it. Nah? I'm confusing you totally. You're not even saying anything. Of course, it's the opposite. Nah? Capacitor blocks DC, and it acts as a short for AC. Alright, now if I go and look here, input signal is connected to the base. I've got a capacitor in between. Why? Because I have a DC voltage here, which I don't want to influence my input signal. Nah? So I block by using this capacitor. It's called a coupling capacitor. Same happens on the output. I can see I've got on the output a capacitor in line with my load, a speaker or whatever. Also don't want the DC voltage to influence my load, my speaker or whatever. Nah? So those two are called coupling capacitors. This capacitor, however, we look at more in the AC way. We've seen capacitor for AC allows the current to flow through, so it acts as a short. So the AC signal will flow through there, but the DC signal will still flow through the resistor because for DC the capacitor blocks DC current. No. So that is called a bypass capacitor, but it refers more to the AC signal. Alright, so now we've established the capacitors as well. We've established that this is a common emitter amplifier configuration amplifier because the input is on the base, the output is on the collector, the remaining terminal in the emitter, so it makes it a common emitter amplifier. Everybody satisfied with that? All clear? Alright. Okay, now if we go and look in our textbooks where we stopped yesterday, we want to look firstly at the DC analysis. Now the DC analysis you basically did in Electronics 1 already. Né? What was the very first thing that you had to calculate when you did the DC analysis, and why? You had to calculate R in at the base firstly. No. Why did you have to calculate R in the base first? Why did you do that? I have to check. The circuit is stiff or not? What does it mean? If it's not stiff, is it like this or what? What does that stiff mean? When you worked out this input resistance, what did you do with this value? You compared it with what? You compared it with R2. And what was the rule? This value has to be at least 10 times larger than the value of R2. If it is, then I can use just the normal voltage divider formula. No. If it wasn't, then I had to include R in base in my calculations. Is that correct? But why did you do it? Or did you just do it like you have to eat and drink every day? Hey? The main difference we want to make here is it should have been done in Electronics 1 already. Electronics 2 is still not too late. I want you to understand the work. You have to understand why you do these things. You were taught a certain amount of knowledge in Electrical Engineering 1, which was very important, as you've already seen, basic knowledge about capacitors. There's another thing that you also were taught there. It was called the loading effect. Who can tell me anything about the loading effect? And don't tell me that you haven't done the loading effect. I just had a look at the syllabi of Electrical Engineering 1. I knew you're not going to know, so I already had a blank page made up for myself here called loading effect. So I'm going to explain it to you, and you will never forget it again. Now, let's take a simple series circuit. You can make a note of this. Here I've got a simple series circuit. Vs, my source voltage. I've got two resistors, R1 and R2. And this will actually count as what? This simple series circuit, what is it? So voltage divider, nah. I even made it easier. If I go and measure the voltage over R2 there's my voltmeter. Here's my voltmeter. And say for instance the voltage that I apply here was 10 volts. Or is 10 volts. What voltage should I measure over R2? 5 volts. Now I made it easy. I made the two resistors the same value. So it should half it. Now if I go and look at my voltage divider formula. V R2. You know the formula says if I want to determine the voltage over R2, then R2 is on top over the total resistance, which is R1 plus R2, and I multiply it with the supply voltage. Now, in this case, it's going to be 1 kilo ohm over 1 plus 1, which is equal to 1 over 2 times 10 volts, so it's a half of 10 volts, which is equal to 5 volts. Now, so there we've proven it. That voltage, that voltmeter should measure is equal to 5 volts. Do you agree? Simple as that. Now, let's have a look at the voltmeter. You've also learned about voltmeters, haven't you? So, a voltmeter, should the internal resistance of a voltmeter, should it be high or should it be low? What says you? Alright, I've got an answer there of low. How many of you say low? Let's do some voting here. Put up your hands if you agree with low. Put up your hands if you agree with high. There's too many people sitting on the fence. You'll have to commit yourselves. I'm going to do it again. If you don't commit yourselves, you'll have to leave the classroom, unfortunately. Alright, let's go with low again. Give me a show of hands for low. I'm looking, I'm seeing who's putting up their hands or not. Who says hi? You didn't put up your hand once, and you put up your hand twice. Only two that says hi. You're the only ones that are correct. Let me explain why. Say for instance, the internal resistance of this voltmeter is low. Say for instance it is my writing on this thing is not so hot. That's 1 kilo ohm, ne? So R2 is 1 kilo ohm. The internal resistance of the voltmeter is also 1 kilo ohm. What is the total resistance of two resistors in parallel of the same value? If I have two resistors of the same value in parallel, what's the total resistance? Half of that, ne? You were also taught that in electrical engineering, ne? So it's 500 ohms, but just to keep it simple for this specific explanation, let's make it 0.5 kilo ohms, ne? 500 ohms. But I will normally express it in engineering notation, of course. And in engineering notation, I don't express anything in 0, something. Now I have to have between 1 and 3 digits before the comma, with the correct metric expression after that. Alright, so now if that total resistance of that section now is 0.5, how is that going to influence my voltage reading? Remember I had here is 1 over 1 plus 1. Now R2 is actually 0.5 over 1 plus 0.5, and that is equal to 1 over 3, isn't it? 1 over 3 times 10 volts is going to give me what? That's not correct, is it? It should have been 5 volts. So what you are actually seeing here is the loading effect. What actually happened? Here I've got my total current. Remember, this is a series circuit, IT. Then it comes to this junction. Kirchhoff's law says it will split. Nah. Then it goes into I of the voltmeter, and it goes into I, splits into I R2 as well. So some of the current will flow through the voltmeter, and some of the current will flow through my load resistor, through the resistor R2. Same amount actually, because both of these resistances are the same, nah. Which is not what I want. I don't want the current to flow through my meter, because I want to make an accurate reading on my voltmeter. So the voltmeter's internal resistance is actually very high. Okay? Normally it's about 20,000 ohms per volt. So if I put it on 10 volts per, the range on my meter on 10 volts, it's 10 times that, so it's quite high. Nah. So let's increase this voltmeter's internal resistance to, say, 100 kilo ohms. Now if I have two resistors in parallel, the one is 1 kilo ohm and the one is 100 kilo ohm. What is the total resistance going to be? What do I know about two resistors in parallel and the one is much larger than the smaller one? The total resistance will always be less than the smallest one, but if the large one is much larger, the total resistance will be very close to the small one. So I would say it would be about 99.99 kilo ohms. No. Ohms, not kilo ohms. So it's 1 kilo ohm, so it's going to be 999.99. Do you agree? So I still have my 1 kilo ohm at R2, so I still have 1 over 1 plus 1, which is 1 over 2 times 10, and I still have my 5 volts. Now I am not loading the circuit. No. So now you're going to ask me, what's this got to do with the circuit that we're busy with? Look at the comparison. Here's my simple series circuit. There's my R1, There's my R2. There's another resistance, my voltmeter. What was the first thing that you calculated? R in at the base. It's that resistance, ne? And that resistance is in parallel with R2. So now you can see if R in at the base is not large enough, I'm loading the circuit and I'm not getting the voltage that I should. Why am I so serious about getting the voltage that I should? Because first thing that we've learned is the transistors characteristic curve. IC VCE, got my load line, and we saw that if I want to bias using R1, R2 to get my Q point in the middle of the load line there. That IBQ is determined by what? VB, ne? Voltage determined by R1 and R2. So if that VB isn't 5 volts anymore and it's 3,3, my Q point is going to be sitting there. There I had my nice signal between cutoff and saturation that I wanted to amplify. Now my Q point is not in the middle anymore, it's down here. What's going to happen? My signal is going to go into cutoff and I have distortion. That is why you work out R in the base first and check if the circuit is stiff or not stiff. Does it make sense? Perfect sense, I would say. Nah. Alright. So now once we've established that, the rest of the stuff you are fairly familiar with. I worked out R in the base. I will compare it with R2 to see if the circuit is stiff or not stiff. Once I've done that, I know which formula to use to determine VB. Ne? I will use VB. If it was stiff, then of course I use the normal voltage divider formula, R2 over R1 plus R2 times VCC to get the value of VB. Once I have the value of VB, I can calculate VE, which is of course is 0.7 volts less. Ne? Because I know there is an approximate 0.7 volt drop between the base and the emitter, ne? For a forward biased PN junction. Is that true? Then I can calculate IE. Why is IE important? What did we learn in the previous section? What do I do with IE when I'm going to do the AC analysis? I want to calculate R accent E. Can you remember? 25 millivolts divided by IE. Ne? So I can get my IE. I can calculate VC, which is VCC minus ICRC. Ne? VC is this voltage here. And of course it will be the supply voltage, VCC minus the volt drop over RC to get that voltage. And VCE is then just VC minus VE. Ne? There I've done my whole DC analysis. Alright. What also is important, which I didn't mention here, is actually the very first thing that you should do. Let me just take this off again. But fortunately it's very simple. It's no problem if I only show it to you now. When I start doing my DC analysis, before I do any calculations actually, I have to draw the DC equivalent circuit. Doing the DC analysis now, ne? I'm going to do the DC analysis, I have to draw the DC equivalent circuit. Why is that important? Because now I've added capacitors to my circuit. Ne? I've got the coupling capacitors and the bypass capacitor as we've discussed. Now remember, we're talking DC now. So DC blocks, ne? The capacitor blocks DC. So what am I saying? This part of the circuit will not count anymore because the current doesn't flow there. Ne? Also here the DC is blocked by that, so that will also not be part of the circuit anymore. And also this will not be a part of the circuit anymore. So if you have to go and draw the DC equivalent circuit, that is what you will be left with. Ne? So if I ask you to draw the DC equivalent circuit because of the influence of the capacitors, that is what I left with. The rest, the capacitor is blocked and there's no current flowing through there. That is figure 6.9 in your textbooks, by the way. And then once you've done that, then you will determine the resistance at the base, input resistance at the base, and then you will do all your calculations. Nah. All clear to you? Simple, nah. All right. Now the next section that we're going to do is the AC analysis. Now this is something new that you haven't discussed before. Let's do the AC analysis. Now again, for the AC analysis, I already know now about the capacitors. Now we've discussed the capacitors already, but remember, now we're talking AC. Now we're talking AC. So capacitors, AC, what happens? Axis is short, normally. Doesn't really 100%, but we will discuss that later. But for simplicity's sake, at this stage, axis is short. At this specific capacitive reactances and so forth. And yeah, then I have to now, the first thing that I have to do is I'll have to draw the AC equivalent circuit. Now, how am I going to do that? Now, fortunately, again, you were taught in Electrical Engineering 1, series parallel circuits and how to simplify them. This is a simple one, actually, you don't have to worry, but let's go to your textbooks first. On page 265, where the heading is AC analysis. There are 2 points mentioned there. Firstly, underline. It says the capacitors C1, C2 and C3 are replaced by effective shorts because their values are selected so that XC is negligible at the signal frequency and can be considered 0 ohms. Alright, important. Second thing there, the DC source is replaced by ground. How's that? Mark the first sentence of the next paragraph as well. It says, a DC voltage source has an internal resistance of nearly 0 ohms because it holds a constant voltage independent of the load, within limits of course. No AC voltage can be developed across it, so it appears as an AC short. That is why a DC source is called an AC ground. Alright, now those two statements, very important when I want to go and draw my AC equivalent circuit. So let's go and do what they said. They said the capacitors now acts as shorts. So let's replace that with a short, C3 with a short, C2 with a short. And let's just draw the supply in again just to make the look of this circuit a bit more simple. So there's VCC, my 12 volts. Okay, so what did they say about that? It also acts as a short. So for AC, the supply is also a short. Alright, now I have to simplify the circuit so that I can see which of these resistors are in parallel and which are in series and what. Of course, I have to do some calculations about these resistances. Okay, the easiest way to approach this is with the 3 terminals of the transistor. So let's start with the base. And I can see here at the base, from the base R2 is connected to ground. But also R1, there's R1, goes there, and it goes through the short also to ground. Do you agree? So what can I do? I can simplify it. I'll take it out there and I can draw it here because it's connected to the base and it's also connected to ground. There's R1 and now I can see that R1 is in parallel with R2. You agree? Alright, let's just simplify. They've just drawn the input signal here. Let's just simplify the input part here as well. There's my input signal also to ground. That resistor is called RS. Doesn't stand for series resistor. It stands for the source. This is internal resistance. So when you see a circuit like this, don't go and look for a resistor of that value. It's the internal resistance of your source. So when you go to the lab and you are issued with all the components to build the circuit, and I can't remember what the signal gen, I think the signal gen there is a 50 ohm internal resistance, and then you must, please don't go to the lab technician and ask him, sir, I didn't get the 50 ohm resistor. Because you won't find it, no? It's the internal resistance of the source. Alright, but anyway, so we sorted out that part of the circuit. Let's have a look at the emitter. I've got a short over here as well. And current is, just like a student, always takes the easiest route, no? So it's going to bypass RE. RE is not going to be part of the circuit anymore. You agree? Because that's a short. Then from the capacitor, I can see via the short of C3, I've got RL, but also RC via this short through the supply, also connected to ground. Now, to simplify it, I can also draw it here. There's the from the collector. Then I can draw that resistor in there, and that is RC. And now I can see that RC is also in parallel with RL, and I can also remove that part of the circuit. And that is my simplified or equivalent AC circuit for this amplifier. Alright, let's go and have a look how they did it in the book. You will find it there on page 265, where it starts. There it is basically. Here you can see the only difference here I see from the sketch that, or from the circuit diagram that I used, they haven't got a load resistor. Now remember, there must be a load resistor in here as well. Because our circuit had a load resistor as well. So that is RL. Alright, you can simplify it even more, of course. I can go and calculate the value of R1 in parallel with R2 and replace it with one resistor. But if I go and do that, I replace it with one resistor, I have to write next to it, né? That is R1 in parallel with R2. And of course the same with RC and RL. If I replace that also with just one resistor, then I must write next to it. That is RC in parallel with RL, né? And remember to use that value then. So, just while we're at it, but we will discuss it again. If I go back to my original circuit over here, say for instance this capacitor wasn't part of the circuit, what was it, C2. The current would have had to go through RE. Do you agree? That will of course also influence my circuit over here, nah. Then I can't just leave it out, then it would have to remain there. Do you agree? So just keep that in mind. Don't go and learn these things like a parrot. You have to go and look at the circuit that you work with. Go and look, is there a capacitor over RE or not? A bypass capacitor. If there's not a bypass capacitor, then of course you have to leave RE in. Like on this circuit, if there was not a load resistor, then I cannot calculate RC over in parallel with RL, because there is no RL. Now, then it will only be RC, for instance. Now, so you have to look at the circuit that you were given to do this. Don't go and memorize this. Understand what you need to do. Work from the circuit that you were given so that you can see what is included and what not. All right. Keep that in mind. Okay, so important here, as you can see here also, the AC source is here in one colored block. Né? The AC source includes then the signal and RS, because it's one thing. Né? RS is the internal source resistance. Okay, why is that important? Why is that important? Here it's even simplified even more. You will find this on page 266, figure 611. You can see it's simplified more. Now, doesn't this look like the loading effect thing that I explained to you. It's a simple series circuit, isn't it? I've got a source voltage here, and I've got an R1 and I've got an R2. I simplified it down to two resistors because I can, or I have to, not only work or determine R in at the base, I have to go one step further, and I have to go and work out R in total, which is now R1 in parallel to R2 in parallel with R in at the base. That equation is at the bottom of page 265. You have to go and work out the complete input resistance, R in total. But now what happens? Remember from here, from my input signal and my total input resistance, I still have my transistor here, Still have my resistor here. So why am I drawing the comparison between the simple series circuit that I explained with the loading effect and this? Because this is also actually a voltage divider. Can you see that? Say for instance I have here a 10 millivolt signal. I have there an R1 and I have there an R2. Is all of that 10 millivolts going to get to the base? Of course not, because it's a voltage divider. Those two resistances are going to divide the voltage. Okay. Alright, so that is what is explained there on page 266. Just below figure 611, as you can see in the figure, the source voltage is divided down by RS, the source resistance, and R in total, so that the signal voltage at the base of the transistor is found by this formula. Remember now, lowercase letters AC voltages, V small b, is equal to R in total. Remember, I want the voltage there between base and ground. So that is VB. Okay, so if I know that's the voltage, then that resistance is on top of the line. R in total divided by total resistance, which is RS plus R in total. That is the ratio for the voltage divider times Vs, which in this case would be the 10 millivolts. And then I will find a voltage less than Vs at the base, because it has been divided by the voltage divider. Alright, clear to everybody? All simple Ohm's laws and Kirchhoff's laws, all boils down to the same old thing. Alright, just please don't go and memorize things. You have to understand what we are doing. We have to understand what we are doing. Alright, the last thing here, the input resistance, or the last thing for today, input resistance at the base. It's exactly what I told you here earlier. If we can go back to our original circuit. But you just clean this this section a bit. You calculated in electronics 1 R in at the base as beta times RE. Is that correct? No, that's the formula that you've learned. And you memorized that formula, And now I've messed it all up, because now I'm using a capacitor. So that resistor is not there anymore. So what are you going to do now to determine R in at the base? It's going to be beta times what? There's no resistance. But we've learned about another resistance, What was that one called? R accent E. So if I bypass everything at the emitter, input resistance R in at the base is going to be beta times R accent E. As a matter of fact, to be absolutely accurate, R in at the base is always equal to that. R in at the base is equal to beta AC. If you don't have AC, of course, you use DC, times R accent E plus RE. That's what it always looks like. But we also use a rule of thumb, and I will point it out to you later again. If R accent E is at least 10 times smaller than RE, then you can neglect it. That's why you neglected it in electronics 1. But actually here, we leave it in, but I will come to the rule of thumb. But in this case now, I can see that RE was bypassed, so RE is not part of the formula anymore. If it's bypassed, then Rin becomes beta AC times R accent E. Do you understand? You have to understand. Don't just memorize the stuff. Anyway, the derivation is there on page 266, where they say R in at the base is equal to V in over I in, which is VB over IB. Base voltage VB is equal to IE R accent E. And since IE is equivalent to IC more or less, IB is equal to IE over beta IC. Then substituting and cancelling, I finally get equation 6.3. R in base is equal to beta AC times R accent E. But you understand now why, ne? I'm not going to ask you to do the derivation. I just ask you to understand why it is beta times R accent E. Are you with me? All right. Then the output resistance, equation 6.4, output resistance is RC. The output is taken at the collector. Ne? What have we learned in the previous section? Actually, you can mark this. It's the sentence just below equation 6.4. R out is actually RC in parallel with R accent C. But what have we learned about R accent C? Is it a small resistance or is it a large resistance? Come on, you should know this by now. Remember in the previous section we said we're going to ignore R accent B because it is very small. And R accent C is very big, nah. So again, I get to, they say here actually it's RC in parallel with R accent C. But we've earlier said if I have a very large resistance in parallel with a not so large resistance, the total resistance is going to be what? Close to the smallest one. Nah. So that's what they say here. Since the internal AC collector resistance of the transistor R accent C is typically much larger than RC, the approximation is usually valid. Let's have a look quickly at example 6.3 and then we're going to end. 6.3 says determine the signal voltage at the base of the transistor in figure 613. This circuit is the AC equivalent of the amplifier in figure 6.8. That's the figure that we've been working with today. Nah? With a 10 millivolts RMS 300 ohm signal. What is that 300 ohm? That's RS, nah? Internal resistance of the source. And then they give us IE was previously found to be 3,8 milliamps. Why do I need IE? What's the first thing that I'm going to do? Calculate R accent E. Nah? So when I go and look at the solution of this problem, I can see R accent E, standard formula 25 millivolts divided by IE, the 3,8, small value, so your calculation is correct, 6,58 ohms. Nah? Again, a small value. Then I can go and calculate R in at the base. RE was bypassed, so R in at the base beta AC times R accent E, and I get a value of 1,0 kilo ohms. Then I go and work out the total input resistance, R1 in parallel with R2 in parallel with R in at the base. In this case, 873 ohms, but, and only when I have the value of RS, can I do the rest. If I haven't got the value of RS, which is going to happen, then you can't do this. You agree with me, nah? So now I can go and calculate VB because I have the value of RS. So RS now acts as a voltage divider with my total input resistance for my source signal. R in total divided by RS plus R in total times VS. So of the 10 millivolts, only 7,44 millivolts reaches the base because of the voltage dividing effect there. Nee. All right. You all clear on that? And that is it for today. So as I say here, you have to read through the section discussed. Work through the examples in the sixth section. Make sure that you understand. Do the relevant true, false. Okay, I spelled wrong there, sorry. That is a typing error. There's a section at the end of the chapter that says true, false quiz, circuit action quiz, and self-test questions. Do the relevant part, and then of course the basic problems also, which up to this stage is problems number 7, 8, and 10. Do not do 9 because question number 9 is not relevant to the work that we covered. All right.